Good afternoon, everyone. I am Ritom from Presidency University BSc second year student. So today we talk about synthesis and characterization of solid state electrolyte NASICON using different precursors. Let's start. Next. Okay, that is the outline of my paper and presentation. And let's start from the beginning. So what is battery? So battery is a device where chemical energy stored and converts into electrical energy and using as a portable power source. So then we'll come to the why we need batteries. So in modern time, we shifted toward the sustainable materials, sustainable energy like wind power, hydropower, solar power, that kind of thing. So in there we have to need batteries because in wind power we cannot get solar power we cannot get it 24 hours, so we have to need batteries also many, and also a power source like mobile phone, laptop and different TVs. In different things we have to need a power source like lithium batteries. And sustainability also as a battery, as a secondary batteries which is rechargeable, so it's used as a sustainable material other than the coal power or other things. Then types of batteries. So there are mainly two types of batteries: is primary battery and secondary battery. You see the examples of the primary battery and secondary batteries. And now today the most commonly used battery in market is the lithium-ion battery and lead acid battery. But there are some lithium disadvantages of lithium-ion batteries and lead acid batteries. Like disadvantages of lithium-ion batteries is like it is very high cost and its abundance is very low, and India has no resource of lithium, and worldwide also very low. Also, lithium-ion is a safety risk concern. It's blast while overheating this, and its lifespan also very limited, and environmental impact. So lithium-ion is a very cost to recycle this material, so that's why it's problematic. And some disadvantages of lead acid batteries is a very low energy density. It's low energy, so it's a very heavier and bulkier than the lithium-ion batteries or other batteries. And it has the shorter lifespan also, and maintenance also needs very to maintain the lead acid battery. And environmental concern. Lead acid are also a very harmful material to the environmental also, and for the for the nature. Then also lead acid battery is a very slow charging rate compared to the lithium ion batteries. So then what is the solution? Solution is come to most our mind is sodium ion batteries. It's a alternative to the lithium ion and lead acid batteries, which is a cost effective alternative. But there are some challenges to use sodium ion batteries, like it's a rapid capacity fading and low performance rate and lower conductivity and low efficiency. That's kind of. So when we talk about batteries, we have to talk about the electrolyte or electrolyte of batteries. So there are different types of electrolyte. Here you see the liquid electrolytes, solid state electrolytes, cell polymer electrolytes, ionic electrolytes, and water salt electrolytes. So mainly I work on solid state electrolyte, particularly in NASICON-type. So NASICON is a type of solid state electrolyte, and it has the high conductivity. It's a stable and strong structural stability. So in NASICON, there are many types of NASICON. You see the element chart. We combine this element chart, and we can create the NASICON solid state electrolyte. I particularly work on NZSP and NH3 Si2PO12. So its conductivity goes around 10 to the power minus 3 s per centimeter to 10 to the power minus 4 s per centimeter. And the structure of the NZSP is it has a ZR O6 octahedral linked with SiO4 and PO4 with tetrahedral arrangement. So it creates the voids to move the Na ions. So the future perspectives in NASICON is the most probable future of SIB batteries, and it can overcome the limitation of solid state batteries also. And it's a sustainable and sustainable material also. Then next, so gap analysis. So we use when we use in research, so we mainly take the chemicals from Sigma Aldrich, which is conferred to the high purity and consistent quality. But there are different types of different types of companies also there which supply the chemicals like CDH, SLR, That's kind of thing, which is come much lower price and cheaper price, but we cannot consider them as a very high quality research. But there are no research or no other thing, but why we prefer the Sigma Aldrich chemicals rather than the CDH chemicals or SLR chemicals. So my object of this project is mainly synthesis of NASICON using Sigma Aldrich precursors and CDH chemicals and characterizing them as structural properties and electrochemical properties of both samples. That's it, and let's start from them. And also we calculate the cost of the precursors to synthesize 2 mole NZSP. You can see the CDH chemicals. Their cost come only 3,333.6 rupees, and other than Sigma is 57,603 rupees. So that's the huge difference. Then methodology. So there are many types of synthesis process to synthesize NZSP, like hydrothermal synthesis and solid method or solid state reaction. Here we use the solid state reaction to synthesize NZSP. Firstly, we took the precursors Na2CO3, ZrO2, SiO2, and NH4H2PO4. Then we measure the components and in molar ratio of 3:4:4:2 and grind it in on mortar vessel for 3 hours. Then we also heated it to evaporate the surface moisturizer and other things for 12 hours in furnace. And then we also calcine this for 1,000 degrees Celsius for 10 hours, and also then again we grind it for 2 hours. Then we go through the pelletization using 13 mm diameter die, and we in a hydraulic press we keep the pressure of 250 kg per centimeter square for 15 minutes. Then we center the pellets in 1,050 degrees centigrade and for 9.3 hours. Then we transfer it desiccator for the further characterization. So result and discussion. So first we talk about the Sigma Aldrich chemical electrochemical properties in electrochemical impedance spectroscopy analysis. So we compare this electrolyte with a circuit. Here you see the circuit resistance and a parallel with resistance and capacitor with a series in constant phase element or the CPE. So then we did the Nyquist Arrhenius plot. You can see in different rate of temperature, and again we plot the time rate of heating graph to see that it is constant, rate of heating is constant or not. And then we plot the Nyquist, which is x-axis is the real axis, which called the Z prime is Z cos theta. Z is the impedance, and Z double prime is the Z sin theta, which is the imaginary part. In here, the left intercept of the x-axis is the very high frequency zone, and the left intercept is called the charge in-grain resistance or bulk resistance, and the radius of the semicircle is called the charge transfer resistance or bulk resistance. Sorry, bulk resistance, grain boundary resistance. Then next, also we calculate the table of the R1, which is the charge transfer resistance, bulk in-grain resistance, and this the charge transfer resistance and the capacity of this in different temperatures. Then we also do the same for CDH chemicals. Also we build a circuit and did the Nyquist Arrhenius plot, and the temperature versus time graph. Then again we did the same thing, and next we did the XRD analysis, which I talk later about this of the two graph comparison. So when we compare this result, so in Arrhenius plot you can see that Sigma Aldrich is much higher than the CDH. It's in the activation energy of the Sigma energy also higher, and from the XRD in Sigma Aldrich chemical we get two phases, which is NZSP phase and ZrO2 phase. On the other hand, in CDH chemical we get the NZSP phase, ZrO2 phase, and also sodium silicate phase. So it is the CDH is more impure than the Sigma Aldrich chemicals. And we calculate the density of these two pellets of CDH and Sigma. You see the density of the CDH is much lower than the Sigma. It means the CDH chemicals sample is much porous. So that's why its resistance also became higher other than the Sigma Aldrich. And also when you see the Nyquist plot, So the impedance of the Sigma Aldrich is much lower compared to the CDH chemical. Then come to the conclusion and it's okay. So we conclusion. So from the Nyquist plot, Sigma CDH CDH chemical precursor samples exhibit a high grain boundary resistance and charge transfer resistance also, and its density is lower than the Sigma Aldrich chemicals. It indicate the impurities and high porosity I've already mentioned, and also for the same in XRT CDH confirms the 3 phases and other the sigma is confirmed 2 phases. And then it's the some reference, and I acknowledge thank to my supervisor and Tina Chandra Singh and Himanshu Bharadwaj to mentor me, my senior, and AC Verma sir and Siksa Sopan team to provide me the internship, and also the Precision team to give the opportunity of this talk. Thank you.
What is the basic output of the project?
Sir, it's the output of the project. We just see this. We can see this for high quality research. We prefer the Sigma Aldrich chemical other than the CDH, because it's come when we use the Sigma Aldrich chemical, it comes 2 phases only, like NZSP and ZrO2. But when we use the CDH suppliers, it comes 3 phases, which is impure. And when you also see this, the density, a CDH chemical is lower density. It means it's higher porosity, which indicates that its resistance also higher than the Sigma Aldrich. But when we use as a battery, we have to down the resistance also. That's why we. Yes. So
I think the crystalline structure.
No, crystalline structure is same, but the phases come, it's a different. So that's why its structure also can be distorted. But the crystal structure is same because we using the chemicals all are same. So density is different. If you see this cost calculation in CDH, you can see the purity. It is lower than the Sigma Aldrich chemical. So that's why the purity. That's why the density come lower. Because when we sintered or calcined, then the impure materials is evaporate.
Can you please go to the material synthesis part, the methodology? Here, that after grinding, can you explain the motive of that step? Which stabilized using 13 millimeter diameter die. Why?
Okay. Okay. So we have to characterize those elements. We have to pelletization. So how we pelletize? We have the device. We use this pelletization technique in hydraulic press. We build a 30 mm die. In this, now we put the powder of the die in the die, and then we press in hydraulic press. We press this, and we make the pellets. Yes, yes. Okay.
So at the beginning, you mentioned about the lithium's abundance in the presence of it, so that it is disadvantageous because we don't have much supply of that. But in creating this type of sample, you are using so many constituents, and if you are producing on a big scale, then how are you going to explain about this element's presence and abundance?
What I can.
How are you gonna support this type of constituents and abundance of this type of elements which you are using here?
No, you can get the sodium carbonate and ZrO2 also available, but when the main material is in battery is lithium. Okay, so but the abundance of lithium is very low compared to the sodium. You can know this, and also sodium is much available than lithium. It's a 350 times much available than lithium.
Can you go to the Nyquist plot that we have? There are 2 plots for Sigma and
Yeah, okay.
In these two plots, there are differences happening in the grade boundary. You see the semicircles, they are shifting. Why this is shifting happening?
Yes, because I can mention the CDH has come the porosity, so that's why its internal resistance also increased compared to the Sigma Aldrich, and you can see this in the diagram also here. The impedance also increase in CDH chemicals compared to the Sigma Aldrich chemicals.
Also, from the Sigma Aldrich, there is one semicircle which is much more shifted than the others.
Because we take it in different temperatures, so that's why its properties also change. Nitrate's properties also change. Yes, because when we use in the real world cases, batteries also goes up to 25 degree to 70 degrees, 90 degree of heating. So that's why we take different.
Exactly, what are the kind of peaks you get?
So XRD, we just get the XRD plot and using some match or expert high score software, and we matches the phase which come, and let's exhibit the CDH chemicals come NZSP, ZrO2, and the sodium silicate phase, and on the other hand, the Sigma Aldrich only come ZrO2 and the NZSP phase. So that's.
As I saw that CDH and Sigma Aldrich have two very different purity contents.
Yes.
One has I think 98 and the other one has 99.99 or something. So is there any other purity in the middle, because the cost difference is huge? So do you know about anything that has?
Yes, there are other chemical supplier like SLR and some others. I cannot recall this name at current time, but other also suppliers. Yeah. Because in that time CDH and Sigma Aldrich is easily available. Sigma Aldrich easily available in all, and also CDH come faster. So that's why we take this. Then,
thank you, Ritom.
Thank you.